Welcome to the fifth lecture, I believe, of the NITheCS SATACS course in category theory. In today's lecture, we're going to look at arithmetic. But this is not the ordinary arithmetic with numbers. This is going to be arithmetic in a category. Let's first go back and revisit ordinary arithmetic, where we have four fundamental entities. The number 0, the operation of addition of natural numbers, the number 1, and the operation of multiplication of natural numbers. Now, of course, these operations are operations on numbers, but they're not just some abstract operations. They come from real world, right? For example, 2 plus 3 corresponds to a real life process of, let's say, combining 2 apples with 3 apples. Now, this process of combining 2 apples with 3 apples, before we count the apples, can also be viewed as a mathematical process where we take a set having 2 elements and we take its union with a set having 3 elements. So let's say the elements of the first are 0 and 1, and the elements of the second are numbers 0, 1, and 2. Now, the difference between the previous picture is that these apples were all different from each other. So when I combine them, I do really get 5 objects. But if I'm trying to get this apple to be red. If I combine these numbers where there are some repetitions, if I put them together, I'm not going to get 5 numbers, right? I'm going to get 3 numbers still, because 0 and 1 is repeated in the 2 sets. But there is something called disjoint union of sets in set theory, which allows you to combine sets in such a way that if there is an overlap, that overlap is kind of disregarded. So what you do is that you let's say you've got these 2 sets you want to combine, you make a copy of the set. In fact, you make a copy of each of them, just to be safe and for the definition to be general and applicable to all situations. And the way you can make copies is that the first copy, you can pair the elements of the first set. You can pair them with, let's say, number 1 to indicate that they come from the first set, and the others you can pair them with number 2. And then we take the union of the two sets. And with this process, we no longer have repetitions, and indeed, the number of elements in the union will be 5, which is 2 plus 3. Now, if we analyze this further, of course, we want to keep track. We definitely want to keep track of which elements in this newly formed sets correspond to which elements in the old ones. Since we renamed the elements, we want to keep track of that renaming, just to be certain what is what and what is meant to be what, and so on. And so that renaming process itself is a function which we can visualize like this. So it maps 0 to the pair 0, 1, and it maps 1 to the pair 1, 1. And in a similar way, on the other side, we've got a function that maps 0 to the pair 0, 2. We've got 1 mapping to the pair 1, 2, and we've got 2 mapping to the pair 2, 2. So if I call this first set x and I call the second set y, I can call the third set x plus y. And I've got these functions that keep track of which elements come from the set x in this new combined set and which elements come from the second set. Let's give names to these functions. Let's call this iota 1 and iota 2. So in the end, I get a diagram, right? This diagram is a diagram in the category of sets, where objects are sets and morphisms are functions between sets. Composition in the category of sets is usual composition of functions. So we can write now that by combining two sets disjointly, so that is ensuring that the copies of the two sets are disjoint from each other, where disjoint means that they don't have an intersection. In other words, the intersection is empty. By combining two sets disjointly, we obtain a diagram in the category of sets. Now, this diagram has a very interesting and a special property. It is, in a sense, a universal diagram. It's a diagram that's universal among all other similar diagrams. And by universal, I mean that if I have another similar diagram, given by some set C and some functions f and g, there will be a unique way to connect x plus y and c by an arrow. I'm going to indicate this arrow with a dashed line to kind of mark that f and g are given before, and then after we're producing this unique arrow. This symbol here represents exists in mathematics, and the exclamation mark is used to say that something is unique. So there exists unique h, but this unique h is not just unique h from this set to C. That's definitely not possible, because you can have a set C having many elements, and then there will be really a lot of ways of mapping elements from x plus y to C. It's unique by certain restrictions. So it's unique when you ask it to be not just a function from x plus y to C, but for it to also satisfy that the composite of h with iota 1 equals f, and the composite of g with iota 2, sorry, yeah, not g, but h. The composite of h with iota 2 also equals g. So I'm claiming that for arbitrary, so let me write this down. So for arbitrary, for this diagram, the one that we constructed above, the diagram of, so the one that I'm now putting in a yellow frame, this diagram, this diagram has the following universal property. The universal property states that given another such diagram, and in fact, given any other such diagram, and I'm going to represent that with a green enclosure. In fact, I want these green enclosures to also contain X and Y, so that the green diagram really looks very similar to the yellow one. Okay, given any other such diagram, and here on the picture we mean the green one, so this could be arbitrary diagram, there exists exactly one sorry, there was some kind of strange sound outside. I just wanted to check everything is fine. There exists exactly one, or in other words, unique morphism H from X plus Y to C with the property that, so it's unique and exists having this property. So there is some H that has this property, and moreover, any other H having the same property will be equal to the one that we know exists. So there will be only one such. Now let's see why this is true. So let's go back to the picture we had here. And let's try to establish that this property is indeed true on an example. So my yellow diagram in this case is this one. And a green diagram would consist of an additional set. Let's say we've got here a set having 4 elements. We can call them 0, 1, 2, and 3. And now I need 2 functions. So here's my x, right? And that's my y. And so and this is my c, and then I need function from x to c. So I could choose it to, for instance, map 0 to 2 and map 1 to 0. So let's call this the blue function. And then let's also draw an orange function that will be from y to c. Let's say y maps 2 to 3. It maps 1 to 1. And it maps 0 to 1 as well. This is our f function, the blue one, and the orange one is our g function. So now I've set up an arbitrary green diagram. So let's put this green enclosure also to link it with the previous picture we had. Here's an arbitrary green diagram. And we now want to confirm that our thesis is right, namely that such H indeed exists in this particular situation, and moreover, that it's unique. Hi, Luca. I think we can hear you now. Let me mute your microphone meanwhile, and when you want to speak, you can unmute it. Okay. I see that Sarah has also joined us. Hi, Sarah. Maybe we can say very briefly for Sarah what we've been doing so far. So we're building what is called disjoint union of two sets. We've got one set here, we've got another one, and now we create a third set that contains copies of the first sets of the elements in the first set and copies of the element in the second set, in such a way that even if the first two sets had some intersection, these new versions of those, they don't intersect, and hence the disjoint union. And the reason why we're doing this, we kind of want to analyze using morphisms the process of adding numbers, because eventually we're going to learn how to add objects in a category. So one thing we observed about addition is that we've got these maps, this one and this one, and so we get a diagram, let's say of this kind, the one that's yellow, and then it has this property that if I have another similar diagram, let's say the green one, there will be a unique way to link these two. I apologize. Can I take just a half-minute break? There are strange sounds outside. I just want to check that everything is going fine there. I'll be back in half a minute. Back and everything is fine. Okay, so the question now is, how do we build a function from the union of these two sets into the set C? So the union of these two sets, we called it x plus y, and we want to build a function h from x plus y to C in such a way that h composed with this function from x to x plus y, which we called iota 1. So h composed with iota 1, it will equal f, and h composed with iota 2, which is the other function that maps y to x plus y, h composed with iota 2 will equal g. Could someone suggest me, how do you think we should define h? So what should we make, for instance, h of 0, 1 equal to, in order for h to satisfy these equalities? Any ideas? So I'm trying to build a function this way. want this function to satisfy this equality. So iota 1 composed with h needs to be f, and I should rather say h composed with iota 1 needs to be f, and h composed with iota 2 also needs to be g. All right, we've got a suggestion there from Joseph that h of 0, 1 should equal to 2. And this is quite a clever suggestion because now let me use pink color for representing the H mapping. So the reason why I want this to be 2 is because this element itself comes from 0 by iota 1. So the 0, 1 is itself iota 1 of 0. Now h evaluated at iota 1 of 0 is of course the same as h composed with iota 1 evaluated at 0. And that I want to be the same as f of 0 by this equality, right? I want that to be f of 0. And f of 0 is, if you trace that blue arrow that starts from 0, you see that f of 0 is equal to 2. So I'm kind of forced for h of 0, 1 to be 2 if I want this to hold. Okay, that's good. We've now defined h of 0, 1. What about the other elements? What about h of 1, 1? Well, we can use a similar strategy there. 1, 1 comes from 1. And so we have to trace where 1 is mapped to by the blue arrow. And we see it mapped to f. So once again, h of 1, 1 equals h of f of 1. Sorry, not f of 1, iota 1 of 1. And that's the same as h composed with iota 1 of 1. And that's the same as f of 1, which is the same as 0. So once again, this forces us to define h that way. Is this clear for everybody? Everybody's happy with this so far? Can you maybe confirm in a chat? And if you're not happy, you can perhaps try to ask a question to clarify, for me to clarify and answer you what you're not happy with. Okay, it seems like everybody's happy. That's good. So in much the same way, we can now define h for all the other elements as well. So the rest of the 3 elements in x plus y are those that come from y by iota 2. And the same logic will apply there. And so I could continue this. And then the general definition of h would be h of xy equals, so when y is 1, this means that we are working with xy's from this piece, right? And then h of that should be defined the same way that f is defined on x. So it equals f of x when y is equal to 1. On the other hand, when the second coordinate is 2, which means that we are on the right-hand side, then we want h to the definition of h to correspond to how g is defined on the components of those pairs. So we will say that this is equal to g of x when y is equal to 2. And this h is of course a function that's well defined. It's impossible for y to be 1 and 2 at the same time. So every xy will have a unique value. That value will be either fx or gx, depending on whether y is 1 or 2. So it's a well-defined function. But moreover, this function is the only function that has the property that h composed with iota 1 equals f, and h composed with iota 2 equals g. So we see here that with this specific choice of f and g, there is a unique way to connect the middle objects so that starting from left, going right and down by composition of functions is the same as going diagonally like this. And the same on the other side, starting from right and going left and down is the same as going diagonally along the orange path. We started with arbitrary f and g. Well, in this case, it was an example, but probably you can see that the same logic can apply in any general case. So we start with our arbitrary f and g, and every f and g produces this unique h. That's a good question that Joseph is asking. Do we show that such a map is unique, or is it because everything is forced? Everything is forced, and that's why it's unique. But if I want to be very detailed in my explanation, I might want to separately formally prove that it will be unique. So I can do this by assuming I've got another h prime, and then these equations will force that h prime to be defined exactly the same way, and hence this h prime equals the h I've defined, and hence they're the same.
Zurab, so, is H an isomorphism, maybe?
H is not an isomorphism because you see, well, in this case, it will be. No, it won't be in this case because H will not be an isomorphism because these two things, as you see from the orange path, these two things will map to the same element.
Mm-hmm.
And an isomorphism needs to be a reversible function, right? So it needs to be injective.
Oh, yeah, okay, I see it now. Okay.
Mm-hmm. So if we go back to our previous concept, this concept of, I mean, the condition we wrote here, it's exactly the kind of condition that gets fulfilled, right? So we said here that so that the sum is a kind of diagram with this iota 1 and iota 2, and it has the property that if I have another similar diagram, then it produces a unique h, which makes these equalities hold. Now, there is another way we can view this, right? Because every h, I mean, we can start with an h. We can have something here, and then it will produce some f and g just by composing that thing with iota 1 and iota 2, right? So every h from x plus y to c will definitely give me two maps, one from x to c and the other from y to c. Just take h and then compose with iota 1 and iota 2. So this will be a mapping that maps such a function to a pair of functions. But now we're saying that if I begin with this, right, there is exactly one that which maps to this by the composition. So what are we saying here? If I draw it on the side, imagine I've got a bag here, a bag of all possible h's. So there's h1, there's h2, there's h3, there's h4. They are just all possible set of all possible maps or functions from, let me rather say functions, set of all possible functions from x plus y to c. On the other side, let's take a bag of all possible pairs of functions. Fg is there as a pair, f prime g prime is there as a pair, and so on. So it's the set of all possible pairs of functions where the first in the pair is a function from x to c, and the second one is a function from y to c. We've got this obvious mapping from the left side to right side. We've got this mapping that maps an h to, so an h gets mapped to the pair h composed with iota 1 and h composed with iota 2, right? Every h here will produce certain f and g by just composing that h with iota 1 and iota 2. Now, when I say that if I start, okay, and that is a function, right? So we get a function this way. The function runs from this set to the other set. So there is a function here, a function. What does it do? It maps h, as we said above, it maps to the pair h composed with iota 1, h composed with iota 2. Now, when I say here that if I start with f and g, right? If I start with f and g, no matter what they are, there will always be unique h such that these composites hold. Basically, what I'm saying is that this function is behaved so that if I pick an arbitrary pair on the right-hand side, there is always a unique h that maps to it. What does that mean? That means that there's a one-to-one correspondence between these h's and the pairs. So we're classifying maps going out of, x plus y via pairs of maps going out of x and out of y respectively. Now, such classification might be new for us, but if we start counting things in this classification, that's not going to be so new anymore. How many functions do we have from x to c? So let me give you a hint to that. There is a special notation for the set of all functions from x to c that gives you a hint as to how many there are such functions. Let me copy this picture, put it on the side here. So this set, the left-hand side one here, is denoted by c to the power x plus y, because they are functions from x plus y to c. Whereas on the right side, we've got pairs of functions. So a function from x to c, the set of all functions from x to c will be denoted by x to the power c to the power x. And the set of all functions from y to c will be denoted by c to the power y. So these pairs will then be elements of the Cartesian product. So in general, a to the power b denotes the set of all functions from b to a. How many are there? Let's say b has 3 elements and a has 5 elements. 1, 2, 3, 4, 5. We can actually visualize it nicely. Let's say the 3 elements of b are 3 apples. Here's 1 apple, here's a second apple, and here's a third apple. And let's say the elements of b are 5 kids. 1, 2, 3, 4, and 5. Okay? So a function can be viewed as a process of giving apples to the kids. And of course, we don't have enough apples, so not everybody will get the apple, unfortunately. So one way we can do this is we can give this apple to that kid, give this apple to that kid, then give this apple to this one, and the other ones don't get anything. Now, every time I hand out the apples, I'm performing a function, right? How many ways can I hand out the apples? What are all possible ways of doing this? Well, you probably know this already. I start with the first apple. I've got 5 choices, right? I can give it to the first kid, to the second kid, third, fourth, or fifth. So I've got 5 choices to make for the first apple. Now, the choices I make for the second apple are independent from the choices I make for the first apple. It's not 5 choose 3, actually. Wait, sorry, is it 5 choose 3? No, it's not 5 choose 3 because, funny enough, I can be very unintelligent and give 2 apples to the same person. That's one reason why it's not 5 choose 3. And the other reason is why it's not 5 choose 3 is because you see these apples, they're all different shapes. So it matters which apple is given to which, because the children will start comparing the apples and they will say, no, I want an apple of that shape. That apple is more shinier. And so it's not just that I have to pick 3 kids that will get the apples. I actually have to assign each apple to each kid. So it's really counting functions here. So 5 choices for the first one is not 5 factorial either, because you see the first apple has 5 choices, but then the second apple, for the second apple, there is again 5 choices. And this is already, once I've given the first 2 apples, I've already decided where the first 2 elements of the set map to by the function. But after that decision, there is still 5 more choices for deciding where the third element gets mapped to. So each time we multiply by another 5. I hope that's clear for everybody. So in the end, we get 5 to the power 3. Joseph, is it clear? Does it make sense to you? Okay, so it's actually 5 to the power 3. And the reason why I said that I would give you a hint by notation is that in this case, this is my set A, and this is my set B. And so we have a formula that the number of elements of the set of functions from B to A is exactly the number of elements of A to the power the number of elements of B. And you might think, okay, this is such a beautiful formula, but actually it's a bit cheating because we designed this notation in such a way to make a formula like this. Okay, so now that we've understood that, let's start counting how many things are there in each of these sets, because according to this one-to-one correspondence between the H's and the pairs of F and G, there must be exactly as many elements on this left-hand side as there are on the right-hand side, right? So what is the number of elements in, so what we know, let's write this down. What we know is that the set of functions from x plus y to c is bijective. There's isomorphism between them, is bijective to the set of functions from x to c, Cartesian product with a set of functions from y to c. And remember that Cartesian product is when you take sets of ordered pairs, because that's what we do here. We take ordered pairs. The first component is a function from x to c. The second component is a function from y to c. So these 2 sets are bijective. They're isomorphic as objects in the category of sets. Okay, how many elements do they have? Well, maybe we don't know it yet, but what we do know is that they have the same number of elements. But we can actually count these elements. What is the number of elements here? According to our orange formula, this is exactly the number of elements in C to the power the number of elements in x plus y, isn't it? It's just applying the orange formula. But we can do better than this, because x plus y puts 2 sets in such a way that they will never overlap. So the number of elements in x plus y will be the number of elements in x plus the number of elements in y. If they did overlap, if some elements were shared, then this would break, right? It would have less than plus. But because they don't overlap, because of this disjoint union idea, the number of elements in x plus y will be exactly the sum of those numbers. So we'll have here x, the number of elements in x plus the number of elements in y. So we've computed the number of elements on the left-hand side here. And by this bijection, we know that's the same as the number of elements on the right-hand side. So let's see what it is. Let's now compute the number of elements here. C to the power x cross C to the power y. How many elements do we have there? Well, Cartesian product, that's easy, right? What is Cartesian product? Let's say you've got ABC and you're pairing them with DE. These are just coordinates, right? You got your you got your AD, you got your BD, you got your CD. I can arrange them in a grid like this, right? You got your AE, you got BE, and you got CE. I can arrange them in a grid, and then I can count them by multiplying the number of things arranged horizontally with the number of things arranged vertically. This is something very familiar to us. That's how we compute area, for instance, right? So in other words, what I want to say is that this is exactly C to the power x times C to the power y. And then we use the orange formula again, and we get this. And finally, this bijection tells us that these two numbers are the same number. Okay, writing A for this part, writing B for this, writing C for that, we get that A to the power B plus C equals A to the power B times A to the power C, right? Fantastic. This is a familiar formula. We know this formula. We know this formula very well. We already learned it at school, right? Now, what is interesting here is that behind this very well-known formula, firstly, there is a bijection of sets, right? And secondly, behind that bijection of sets, there is this property, this universal property that I called this property here, which says that a sum of two things must be a diagram like this, such that for every other diagram, there is unique H, such that these two hold. And the reason why we want this property is because we can now use this property to define sum of two objects in an arbitrary category. So far, we've been working in the category of sets, and we wanted to, what was our initial goal? We want to somehow capture the idea of addition of numbers. And we express this by thinking of numbers as quantity of elements in sets. And then that's how we came up with this diagrammatic condition. But now the amazing thing is that if we state the same, exactly the same diagrammatic condition in a general category, we get a concept of addition of objects in a category that turns out to work in many very important examples of categories. So let's write this definition out. Now, as stated in a general category, in a category, let's call the category C, even though this shouldn't be confused with complex numbers. In a category C, the sum of two objects, X and Y, is a diagram of this kind, such that for any other or the same, for any diagram that also consists of the X and the Y and the C, for any diagram with F and G, there always exists a unique H morphism from X plus Y to C, such that H composed with iota 1 equals F, and H composed with iota 2 equals G. So the new term we're introducing here is sum, even though it looks very familiar because we know sum of numbers, but this is no longer sum of numbers. This is sum of two objects in a general category. Is this definition clear? Is everybody happy so far, or do you want to ask any questions about this? Let me give you some moments to reflect on this, and let me know if you want to ask something.
No, I think it's clear.
Okay, fantastic, fantastic. There are a lot of things we can do and we want to do with this. The first thing we can do is to define sum of not two, but many objects, several objects, not just two, but maybe 3, 5, or maybe even 1 or 0. So let's actually do that. I'm not going to write out the formal definition for many. I'm just going to draw more pictures. So imagine now instead of two objects, we have several. Let's say we have x1, x2, x3. So overall, let's say we have a family of objects, xi, indexed by index set I. So this notation simply means that I is some set, and for every element I in I, we are choosing some specific object xi in the category. We call such a thing a family of objects. So consider a family of objects. This is our starting point. And here on the left side is a picture. Let's say in this example, we have 3 of them. So in this example, I equals the set of 1, 2, 3. There's too many commas there, sorry. 1, 2, 3. Now, how do we define sum of 3 objects? Well, it will be very similar to sum of 2 objects. With the sum of 2 objects, we took 2 objects and we kind of put them together, and we had these maps that trace where the elements go to when we put them together and when we make copies so that things are disjoint from each other. So here we have 3 of them, and so we'll just do exactly the same thing, but now it will be with 3 things. So the sum of xi, where I goes from 1 to 3, will be defined as a diagram of this sort. So now I will have iota 1, iota 2, and iota 3. The condition on this diagram will also be similar to the previous one, whereby we'll say that for every other, or for every similar diagram, so let me represent that with yellow morphisms. So for any diagram of a similar kind, given by 3 things, this time we can call them F1, F2, and F3 before we call them F and G. Maybe now it's better to call them F1, F2, and F3 so that they're indexed by the same index of as the X has. And so we also need the C. For every C and every F1, F2, F3, so this is for every, right? There must exist a unique, let me use blue for that. There must exist a unique way of connecting these, but with the property that composed with iotas, it gives corresponding Fs. So there exists unique H such that for every I in my index set, which is I, right? For every I in I, H composed with iota I equals Fi. So what does that mean? So what does this symbol mean? I'm sure you know what the symbol means, but for the sake of completeness, let me remind you what it means. It really means that we want this equality to be true for every single value of small I. So in this our example, it does mean that we want H composed with iota 1 equal F1, H composed with iota 2 equal F2, and H composed with iota 3 equal F3. If we didn't have the 3, if we didn't have F3 and iota 3, right, then this would be exactly the same condition we already defined before. So we get a notion of sum of 3 objects. So now, if I have a family, I can define sum of this family is defined by exactly a similar kind of diagram. So what is it? It is given by some object that will be called summation of xi's, where I belongs to I. And it will have a family of iotas. So let's call them iota j's, right? Or maybe I can even call them i's. I just don't want to use the same script I used there. Iota j's, which go from xj's. So there is one for every j, right? And then the condition is that for every other family of such fj's that now go from xj to c, there exists a unique h that is such that for every j, and j is still element of my index set I, for every j, h composed with iota j equals fj. Is this clear as well for everyone? We've got 2 thumbs up. What about Luca and Sarah? Joseph, you made a comment just taking Y to be the empty set. What do you mean by that? Or was it from a different? Oh, wait, maybe that's an old comment. Sorry. Which one looks like half the diagram? This one here. Oh, you see. So I only drew, like in the previous diagram, we have 3 of them, right? So imagine I had only drawn one of them to represent all 3. That's why I put the J here. Because I don't know how many there are, because now I is an abstract set. So I can't really draw them. But I'm drawing just one representative. Just one representative. I actually want to have many of them, as many as there are elements in I. So that was a good question that you asked there. There is an interesting special case of this, actually. A special case when I is the empty set. So let's look at what happens when I is the empty set. When I itself, the index set itself, is the empty set, what happens then? The family xi, in that case, will have nothing in it, right? Because we were supposed to have one xi for every small I. But now these small i's must belong to the big I, and the big I is the empty set. So there being nothing in big I, there is no small I, and hence there is no xi. So this is what is called the empty family. This is then the empty family. if we have an empty family, are we still going to have the sum? Well, it will be called the empty sum, but it will still be an object of the category. So it will be a sum of xi's where I ranges from the empty set. In other words, there are no xi's, but this is still going to be an object. What is the condition that it will satisfy? Well, the condition says, according to the picture here, that for every yellow diagram, but what becomes of the yellow diagram when there are no j's? The index set AI is empty, so there are no j's, right? And so if there are no j's, there are no xj's, there are no fj's, but there is still a c. So now the condition says for every c, there exists unique h. And what condition is h unique under? We said that here we said there exists unique h such that this holds for every j in I, right? But when I is the empty set, this will be trivially true, right? There is nothing in I, so it is trivially true to say that everything in I will make this hold because there is nothing in there. If I say everybody in the empty room likes ice cream, you can't take me to court for lying. If you would want to take me to court for lying, you would have to find someone in the empty room that doesn't like ice cream. Then you can say, well, you said everybody likes ice cream, but this person here doesn't, so you lied. But the room is empty. So if I didn't lie, then I told the truth. So the condition becomes that the empty sum is a certain object in the category, so that for every other object, there is a unique morphism from this object to that one. The condition simplifies considerably. Let's write this down. We get, so in this case, when I is empty, we get the concept of an initial object. So what is the definition of an initial object? An object X, let me call it something else. An object, I would have called it I, but now we used I for the index set, so I don't want to call I. An object, let's say A, is said to be an initial object when for any object C, there exists exactly one morphism from A to C. There exists a unique morphism from A to C. This is something weird, right? What would this correspond to the usual arithmetic when the sum of objects becomes sort of the usual addition of numbers, at least in terms of the quantity of elements in the sum? Well, it should be some kind of empty sum of numbers. If I take no numbers and I add them, what number do I get? What do you think is the answer to that question? Is there empty sum of numbers? And if yes, if you think there is such a thing, what is it equal to? Oh, that's a good one, Okwatsia. Sorry, I didn't pronounce Okwatisa. That's a good one. It equals to 0. Empty sum is 0. Similarly, empty product is 1. If this is a new idea for you, you should let me know and we can talk about this. Otherwise, I'm going to now suggest that perhaps this should be the set which has zero many elements, right? If we want this counting strategy to work. So then it would make the empty set be the initial object in the category. Let's prove that. Here we've got a theorem. In the category of sets, the empty set is an initial object over it is the only initial object. There is no other. There's only one initial object in the category of sets. Let's at least sketch the proof. So in the category of sets, being initial means that for every other set C, there must exist unique function from unique function H from the empty set to C. Is that true? Now you might wonder, how can that be true? How can there exist a function because there is nothing here, right? Well, there is a formal definition of a function according to which it will exist, H will exist, but there is also intuitive definition according to which it will exist. Imagine you work in a library and every morning after all the books that people have been reading before, every morning you want to collect these books and put them back in their shelves. Maybe they didn't put them back on the shelves, those who visit the library. So before the library opens, you want to put all the books that have been read and that have been misplaced, you want them to put them back in their original position. So you've got a set of books. So maybe there is a book there about the interaction of mathematics and music. There is a book about category theory. There is a book about fashion, and so on. And you want to put them on shelves. So these are the shelves. Once you're done with that task, right? Once you put the books on the shelves, then you can open the library and new guests can come in. You don't want to bring the new guests in because you first want to clean up your library before you bring in the guests. So every morning, you're establishing a function. You're establishing a function from the set of books to the set of shelves. And once you place those books on the shelves, you consider that morning part of your job done, you feel good about it, and you move on with the day. Now, what happens when the previous day there were no visitors, so no books have been misplaced, so the set of books is empty? You would still feel happy, right? You didn't do anything. You didn't have to do anything. Maybe you just had to just check that there are no books misplaced, but otherwise, you didn't have to take the books to the shelves. You will still feel happy, and you will still feel that you did your job before opening the library. Now, that feeling that you have of having done your job is a kind of real-life manifestation of the existence of this function from the empty set to any other set C. In this case, C is the set of shelves. Formally speaking, a function is defined as a set of ordered pairs. Recall that a function in general, between any two sets, let's say any two sets A and B, is a subset of the Cartesian product. Let's call this subset something. Is a subset S of the Cartesian product A cross B, such that for every S, there exists unique B. Sorry, I should have said for every A. For every A, there exists unique B in B, such that the pair AB belongs to S. Every book has to be placed on a unique shelf. You can't place the same book on two different shelves, right? And you can't either not place a book. Every book has to be placed somewhere. Moreover, every book has to be placed in exactly one shelf. So that's what we're saying here. For every A, there exists unique B. And I'm encoding this information of which book went into which shelf by a set of ordered pairs. So here are the books, here are the corresponding shelves. So that's what a function is in general. Now, what happens if in this definition A turns out to be empty set? If A is the empty set, then the A times B, which is then the empty set times B, has only one subset. Possible values of S is only one, and it is the empty set, because when you try to collect ordered pairs where the first component comes from the empty set, since empty set has nothing in it, there will be no ordered pairs. So it has only one subset, the empty set. Does that subset fulfill this requirement that for every A there exists unique B? For every A in the empty set, so the statement that for every A in the empty set there is unique B in B such that the pair AB belongs to the S, which in this case is the empty set. This thing is vacuously true. And I'm not sure about the spelling of vacuously, so I'm trying to get help from the computer with that. It is vacuously true. There we go. Because there is nothing in it's the same reason why you wouldn't be able to take me to court if I said that everybody in empty room likes ice cream. Because there is nothing in the empty set, we will never be able to break this condition. To break conditions saying for everything inside the empty set something is true, I would first have to find something in the empty set for which what follows would have been false. But I can never find anything in the empty set, so I can never break it. Therefore, this thing is true. So this unique possibility of a function is indeed a function because it satisfies this criteria that for every A there exists unique B such that so and so. And that's called the empty function. And we denote it by the empty set because it is the empty set as a set of ordered pairs. And that is our unique function then from the empty set to C. Any questions on this one? All right, I'm glad to see that You're comfortable with this idea? So, so what we've done so far is to look into this concept, the concept of a sum of objects in a category, which turns out to capture not only addition of two numbers in terms of the quantity of elements in the sets viewed as objects in the category of sets, but so not only addition, but also number 0 is captured here. Number 0 is captured by an initial object. If I go back to the beginning of my lecture where I said that we want to extend arithmetic from numbers to general categories, we know already now how to deal with this part of the picture. Let me draw multiplication here this way. So the next thing is to see what to do with the other one. Are we going to define multiplication, and how are we going to define an object that mimics the behavior of number 1? So maybe, because it seemed like the number 0 being represented by the empty sets exhibits a very simple type of behavior, maybe we can get lucky and we could maybe try to see if we can identify a property that defines a set having only one element, which is what would represent number 1, right? So after all of this that we discussed, where we eventually reached nice notion of addition in the category, how do you think we should define number 1? So what do you think makes a one-element set special among all other sets? We now want to capture a category theoretic property of a one-element set. So let's draw a one-element set. A set having its unique element, let's say a star. The property needs to be stated in the language of morphisms between sets. So this would be probably morphisms that connect one element set with other sets. Any ideas come to mind? Let's remind ourselves that to do the same thing for the empty set, we just have to say that for every other set, or for every set in general, C, that it always exists unique function from empty set to C. We didn't prove yet that every initial object will be empty. We did prove that empty set is initial, but we didn't prove yet that every initial will be empty. But that's sort of easy to see, because imagine if you've got an object A that has exactly one function to every other set. I will pick a set with 2 elements, right? Now, surely I can map every element of A to 1, and I can also map every element of A to 2, and I will immediately get 2 different functions. Unless there's nothing in A, of course, but then that's the empty set. So as soon as A is not empty, I won't be able to get this property that there is exactly one function to each other set. So that's proving the other side, which we forgot to do. So empty set can really be characterized by this property that for every set C, there exists exactly one function from the empty set to C. What is a characteristic property of the singleton set? Any ideas? Well, the singleton set has an identity morphism, just like every set does. How is that characteristic? Every set has an identity morphism, right? Everything can be mapped onto itself, and we get an identity morphism. In a category in general, every object has its own identity morphism. I don't see yet how it is characteristic to the singleton set.
Isn't it the only morphism, like there's no other morphism we can take?
From here to itself.
Yeah, from here to itself, yes, or maybe to another singleton.
That's a very good idea, indeed. If I mean, fantastic idea, because as soon as this set has two elements, right, I would always be able to have at least two functions. Let's say map 1 to 1 to 2 2, and then swap them around, right? So it seems like this could be a characteristic property that is exactly one function from this set to itself. However, there is one thing that breaks it. The same is true for the empty set. There is exactly one function from the empty set to itself. It's the empty function. I mean, there must be exactly one. We already said from empty set to every other thing is exactly one. So in particular, when I take C equals empty set, I get there is exactly one function from empty set to empty set. So now we want to distinguish one element set from the empty set. And we already have distinguished this from all the other sets that are non-empty, because indeed you're right that among non-empty sets, this will be the only ones that, I mean, the singletons will be the only ones that have exactly one function going from it to itself. But how do we now distinguish between this and that? So it's not enough to say that there is exactly one function this way, because that property holds for the empty set as well. Any ideas? We're very close. We're very close. It's a very good lead to think of there being exactly one function from the singleton to itself. We want to somehow distinguish these two, right? Because this one also has exactly one function. What if we try to somehow compare them? Let's compare the empty set and the singleton with each other. Maybe that will give us some ideas. If I want to tell two things apart from each other, it's natural for me to compare them, right? Well, but in a category, how can we compare two objects? I guess by examining what morphisms there are, right? So because empty set is initial, of course, we know that we've got this function. We have unique function from the empty set to the singleton. Do we have a function going backwards? Do we have a function going this way? Does this function exist? Will I be able to define a function from the singleton set to the empty set? What do you think about that? I will have to specify this value, right? I will have to say what is f of star equal to. How can I define f of star? Any ideas? It's a good question, Yusuf. It's a very good question. You see, or quite easily, if we put f star equals 0, we're in trouble, because whatever we put here, right, that has to be element of the other set where our function goes into. If you put f star equals 0, then 0 has to be element of this, but the empty set is no elements. So we can't actually put anything here because there are no elements. We are forced to put something here because there are elements in the domain of f, but there is nothing in the what's called the codomain of f. And so we fail to assign star to something in the empty set because there's nothing in the empty set. And therefore there is no function going backwards. And that's interesting because now we see that there's a function going from the empty set to the singleton set, but there's nothing going backwards. Can maybe that give us an idea how to adjust slightly our previous idea that we could have characterized a singleton as a set such that there is exactly one function going from this set to itself. Let me give you some time to think. It's an interesting moment, I think. It will be nice to discover this yourself instead of me telling you. So give it some thought. You can just suggest what we can try. It might not work. That's fine. We can go through a few suggestions before we find something that works. Oh, the question is we want to find a property of the singleton set that only the singleton set will have that property. Like here, the empty set is the only one that has the property that for every C, there exists a unique function. Now we want to find a property that only singleton sets have, a property that's expressible in the language of the category of sets. Previously, we said that this property should be that exists exactly one function from the singleton to itself. But that property doesn't distinguish only the singleton because the empty set also has that property. So what property would distinguish the singleton? Well, we did observe that there is a function going this way, but there is nothing going backwards. Maybe that can give us an idea together with this idea that there is exactly one thing going here.
Maybe composing it with another function would give you that function again. But no, okay, no.
Composing what with another function? Don't give up on it. It seems like an interesting idea. Composing what?
Composing a function from the singleton set to another object, and then we take another one, an arbitrary, and then that diagram commutes, but I don't have it.
Like
I don't have
this?
the picture.
Like this?
Yeah, and then maybe there's another Y, another
Like this?
object. Okay, yeah. So composition of G and F would be what?
Well, it would be a constant function, right?
Okay. Yeah, that's as far as I can see it.
What would G be?
So everything in Y will be mapped to the singleton.
Oh, so there's only one way to build G. Is there only one way to build G? Can there be another function? Sorry, I need to write a star here. Can there be another function from Y to singleton?
No, because it's the well-definedness doesn't allow us to, yeah.
What if we try that then? It's kind of opposite to the other one, right? So what if we try that? We say that there exists exactly one function going this way. For every set y, there is exactly one thing going there. The singleton fulfills it, right? No matter what set y we pick, no matter what this is, there will always exist unique this, right? Because everything has to be mapped to singleton. There is no other choice, right? Okay. Would the singleton be the only one that fulfills it? If I had two elements here, would it still be true that for every y there exists unique function here? Probably not, because I could map everything to 1 and then I could map everything to 2, right?
Yeah, yeah.
So it seems like if as soon as there's more than one element here, there will be more functions. But now let's check the empty case, because previously the empty case. So it's like this the condition we had before where we said that there is exactly one function this way, but now we're saying there is exactly one function not only from singleton to itself, but also from every other set to itself. And if I put the empty set, is that true? Is it then true that for every y there is exactly one function here? And I think we just saw that it's not true because we said that from singleton to y to empty set there's nothing, right?
Yes, so yeah, I think,
So I think we got it right,
yeah.
because this property seems no longer to be true for the empty set or sets with more than one element. This brings us to the notion of a terminal object. A terminal object in a category is an object, let's see T, such that for any object y, there exists unique function morphism. There exists unique morphism from y to t. Now Joseph makes an excellent remark there. He says, like the singleton basically acts the opposite to the empty set. And that's a fantastic remark, Joseph, because it does, right? Whatever we said about the empty set, here it holds exactly the same, but the direction of arrow has changed. Now it's no longer that there are unique functions going out of it, but there are unique functions going into it. And this fantastic observation, we can try to borrow this now with maybe we're like too optimistic, but we can try to borrow this idea, and to define product in a category of objects, we could maybe take the definition of sum and make all the arrows go the reverse direction, just like it happens here. So let's see what happens if we do that. So let me copy the definition of a sum, and then we're going to reverse all the arrows and see what we get. I'll just work in the case of 2 for now, 2 objects. So here was the, okay, maybe this is too small. Let me redraw it. So so here's the question. So first let's write down Joseph's remark. Notice that a terminal object is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let's say that the object y is defined in an opposite way, whatever that means, from the object y. So let to an initial object. And the question we're asking, could we perhaps get the definition of product, definition of a product in a category, by taking the opposite of the definition of a sum, by considering the opposite of the definition of a sum. The opposite of the definition of a sum. So let's try that out. Let's recall the diagram for sum. We've got a diagram. We had a diagram like this. Iota 1, iota 2. Then there was this arbitrary C, arbitrary F, and arbitrary G. And then we were saying that there exists unique H. And the requirement was that H composed with iota 1 is F, and H composed with iota 2 is G. What happens now if we take this exact same definition and we apply your idea to it, Joseph? So I'm going to draw the new arrows, the reversed arrows. I'm going to mark them yellow so we can tell the track which arrows have been reversed and which haven't been reversed. So here I get a yellow arrow in backward direction. I'm going to erase the tail of this old one. And the arrowhead, which has now become the tail. Let's erase this arrowhead and instead draw a yellow arrow going this way. Let's do the same thing here. Arrowhead there, arrowhead here. And then we erase those tails. But now we want them to be yellow, right? Oops, that's black, sorry. Here is one. Here's the other one. And then this H should also be reversed. But we have to be now careful with these equations because H can no longer be composed with iota 1 in the order that's written here. Since the arrows got reversed, the composition will also reverse. It's first H and then iota 1, which in the composition expression, it should swap around. And so it should be H composed with, sorry, it should be iota 1 composed with H equals F, and iota 2 composed with H equals G, instead of this. So they change to that. Well, we're hoping, and maybe we are too naive to hope that, but we're hoping that this will give us a good notion of product of two objects. We can test this idea numerically. Remember how this definition had a manifestation in terms of a law of exponentials of numbers. Let me remind you what it was. The number of elements. So the set c to the power x plus y being bijective to c to the power x cross c to the power y, which in terms of numbers of elements gives us that this number to the power that number plus that number is the same as this number to the power the first one of those, and then that multiplied by that number to the power the second of those. And somehow this rule already kind of gives us a hint that this condition should be satisfiable. And so let's establish, let's look at a similar formula that arises from this diagram, and maybe we can tell from there that whether our guess is good or not. But of course, afterwards, we still want to would want to prove that this does give a good notion of product. So what would be the corresponding bijection formula here? This time, the set of h's, they are functions from c to x cross y. So we would write them as x cross y to the power c, right? Remember, functions from b to a are written a to the power b. Okay, so that's the set of h's. And according to this definition, just like before, this set will be in bijection with the set of ordered pairs fg. So this is bijection in bijection with what? The set of these functions. So that's functions from c to x. So that's going to be x to the power c. Cartesian product with the set of these functions, which is y to the power c. And the numerical version of that is going to be that the number of elements in x multiplied by the number of elements in y to the power number of elements in c is equal to the number of elements in x to the power number of elements in c multiplied by the number of elements in y to the power number of elements in c. Is this something familiar? Is this formula true for numbers? It sure is, right?
Yeah, what is it? Exponentiation, yes.
Yeah, sure is. Oh, this is fantastic news. So perhaps we will indeed be able to prove that this property does define multiplication for numbers, in other words, for sets. What is behind multiplication of numbers in set theory? We already talked about that. It's Cartesian product, right? So now our attempt will be to show that in here, this will really be Cartesian product of sets. Well, if this were to be Cartesian product, what would these iota 1 and iota 2 should be? We should still decide what they are before we start checking that they have a good property, right? If I have a pair xy, how can I naturally assign to this pair an x and a y? It might not be the same, but maybe it should be the same. What would be a natural way of taking a pair xy and producing an element of x out of it, where the pair was consisting of an element of x and an element of y, right? Wouldn't it be most natural to map this to the first coordinate and map on the other side to map that to the second coordinate? Well, if we do that, we should probably call these maps not iotas, but pi's. They're projection maps. So let's call them so. Pi 1 and pi 2. And let's revise our formulas with pi's inserted in the place of iotas. Pi 1 and pi 2. Let me still denote them with yellow color. Okay, fantastic. Now that we have an idea what this pi, let's check that the condition holds, that for every f and g, there will indeed exist such unique h. Okay. So let me copy this picture. Copy it here. And let's also copy these equations. And let's start thinking about this. Let's first explore what these equations say if I start evaluating both sides on elements in C. With the first equation says pi 1 evaluated at h of C, right? Pi 1 composed with h evaluated at C is the same as pi 1 of h of C. That, it says, should be the same as f of C. The other one says pi 2 of h of C must be g of C, right? But what is pi 1? H of C is some ordered pair, right? Because h is a function from C to x cross y. So the value of this function will be some element of x cross y. Now, pi1 is the first coordinate of that ordered pair, isn't it? This is what pi1 does. It maps an ordered pair to its first coordinate. So this equation is telling us that the first coordinate of this ordered pair is f of c, doesn't it? In a similar way, the other equation is telling us that the second coordinate of the pair is g of c. So this equation is forced by these equalities. So for sure we know that there is at most one h, but is there at least one h? How to define it? Well, we've got in front of us the definition. Define h of c to equal the pair f of c, g of c. So this equality defines h. It defines unique h because it is forced. Defines unique h from c to x cross y such that pi1 composed with h equals f and pi2 composed with h equals g. Does this make sense? Any questions? Thanks for your comment, Joseph. Just for others to hear it as well. You said that you always wondered what these diagrams were, and now it's quite intuitive. Yeah, they're quite famous diagrams because um, the definition of product was formulated in very early on in category theory. It was a paper of Saunders MacLean. So category theory was invented by Samuel Ellenberg and Saunders MacLean, right? So they wrote a paper in 1945. And then a couple of years later, or 3 years later, Saunders MacLean started exploring the category of groups, and he had this wrote this paper about how when you reverse arrows, you get interesting properties from other properties. And in the same paper, he also drew a diagram like this. They had different labels than what we use here with F and G. Instead of that, I think there's alpha and beta. And so he defined a product of two objects. And because the product was defined so early on, it kind of became as a typical diagram one would use when one wants to draw a picture of category theory. Isn't it interesting how, okay, before I move on, let me ask also, Okwatisa, are you happy with what we discussed, or is there something that's a bit blurry in this?
No, I think yeah, this was a good introduction because when I was listening to Dr. Ghosh, he will always start with products, and then I would never have this kind of firm grasp, but this kind of helps. So yeah.
Okay, that's great. So what is interesting about this is also that this whole story, right? So this definition, it is a story how it links up with these exponential formulas, right? Then there is a story of how the product and the sum are linked by reversal of arrows, right? And then there is a story of how the sum itself links up with another form of exponential formulas. And all of this together, pieced together, kind of gives, I think, a nice insight into arithmetic, completely new insight into arithmetic, because people before wouldn't really have thought of relating numbers in terms of functions between sets of corresponding sizes. But now it turns out that relating numbers using these arrows is quite useful because it allows you to transfer ordinary arithmetic into arithmetic inside a category. And we don't have too much time to discuss it now, but let me mention briefly that when we take other categories, not of sets, but of other structures, these notions of sum and product, in most cases, are very useful. They allow us, they describe constructions that allow us to build mathematical structures from known structures. Of course, a typical example is the real numbers, R cross R, something we've seen a lot, right? This R cross R, we can think of it as a vector space, because usually when we talk about R cross R, we think of the Cartesian plane, right? But it's a vector space. This vector space turns out to be product of the vector space R, of the one-dimensional vector space R, with itself, inside the category of vector spaces, where objects are vector spaces, morphisms are linear maps, and composition is the usual composition of maps. Another example, if you take two topological spaces, if you know what they are, and you take their categorical product, so the product inside the category where objects are topological spaces, morphisms are continuous functions, and composition is the usual composition of functions. That gives you exactly what in topology is called. So you take Cartesian product of the underlying sets, and then you put a topology on it, and that's exactly the product of topology that topologists define. So it's remarkable that in so many different examples like these two and many others as well, these concepts of product and sum are as important and as meaningful and as useful in the corresponding disciplines as the multiplication and addition is for numbers. So we have this form of some kind of generalized or higher. Sometimes people use the word higher to refer to process of turning a set into a category, and then it can go on. You can turn a category into two-dimensional category and so on. So we can call this thing some kind of higher arithmetic that now works inside general categories and hence is applicable to many other categories as well than just the one of sets, which allows us to recover arithmetic of numbers. Fantastic.
Zurab, do you mind sharing maybe what those papers by McLean on the group? Is that something which is possible?
Absolutely. Absolutely. So the paper by McLean is called Duality for Groups, and I can I think it's possible to easily get it on Google, so I'll do it and then I'll share it on the group.
Thank you.
This brings us to the end of the lecture. The next one, most likely, we will explore these sums and products further. We will establish some nice properties they have. We can establish their commutative, their associative, just like number arithmetic, addition, and multiplication. The only difference will be that now there will be commutative and associative up to isomorphisms. Even the terminal object, we saw that the singleton sets are terminal objects, but we can have many different singleton sets depending on what the element is, right? But they will all be bijective to each other, in other words, all be isomorphic to each other. The uniqueness of the initial object was something very specific because there's only one empty set, but there are many sets having one element in it. So A cross B, another example, A Cartesian product with B is not quite exactly the same as B cross A because one has pairs A, B in it as elements, and the other has pairs BA in it. So A, B, and B are not exactly the same, but there's a bijection between them. So we will see how these standard laws of arithmetic apply in the more abstract scenario, but equalities become replaced with isomorphisms there. And then there are also many other examples of sum and product, those that are familiar to us, that can be linked to these general notions. That is certainly worth discussing. So all of that in the following lectures. And for now, thanks for joining, and we will meet again next Saturday.